Hi everyone, my name is Daniele Tramontano and the work that I'm presenting is called the Learning Linear Non-Gaussian Polytree models. The problem that we study is the classical structural learning problem, so we want to find G underlying a given structural causal model starting from observational data. To ensure both scalability and identifiability, we assume that the graph is a polytree and that we work in a linear non-Gaussian setting. We propose a two-step approach. In the first one, we learn the skeleton of the graph using the classical Choudhury algorithm, while we propose three different orientation schemes. All the orientation schemes leverage on algebraic relations that we found among the cumulant of the distribution. In particular, we assign to each potential edge an orientation matrix, and we prove that if the edge actually belongs to the graph, that the rank of this matrix is 1, while if you take the same edge but with reversed orientation, the rank of this matrix is 2. To understand how this works, let's look at the simple example. We have an edge from 1 to 2, and then we see that the orientation matrix in this case is rank 1, and you can see that the second row is proportional to the first one, while the matrix associated to the other orientation in general is rank 2. So leveraging on these properties and on the classical B-structure search that is made testing for independence of the variables, we build three different orientation schemes that differ from each other on the amount of information that they get from pairwise orientation against the information that they get from independence testing. We have a consistency result, but I will skip on this in the interest of time, but from the simulations you can see that even in the setting where the sample size grows lower than the size of the tree, you still converges to the right tree, and moreover you can see that the algorithm that performs the best is the one that only uses pairwise orientation, and this is due to the fact that this algorithm does not allow for any kind of propagation error that you instead have when you test for independence. This is it for the moment, and thank you for the attention.